fraction equal fraction, did some cross multiplying and going. I tended to do it a little bit differently, a little bit more systematic, because it just always worked. Or made it straight from the ordinary. Now, we're talking about here with arc length. Again, your arc length is going to be your central angle times your radius. And that central angle is theta, and theta has to be in radians. Now, if it's in radians, it means it's going to have what with it? Pi. Very good. It'll have pi with it. So, for example, if I say that I have a circle, radius of 4, and I want to find the arc length with something that is a 40 degrees, I have to convert 40 degrees to radians. By how? What was it? Yeah, I was waiting to make sure you said yeah. Multiply it by pi over 180. So in this case here, it's going to be 4 times 40 times pi over 180. See what I'm doing there? All I'm doing is just setting it up to convert it from degrees to radians. Before I go any further, can I simplify that right away? What can I knock out?
Zeros and divided by 2.
Good. I can knock out the zeros. This becomes a 9. This becomes a 2. So I get 8 pi over 9. And that's my arc length. Not so bad. It's exactly where you're taking the chunk off the circumference. It's just another quick one. All right. And if you're in degrees, you don't have to worry about it. If you're in degrees, you switch to radians. If it's already given to you in radians, it's just a matter of substitution. Yeah. Same thing goes for if you're looking at the area of the sector. Again, the only thing that changes here is you just take 1/2 the radius squared times theta. Again, theta will be in radians. It's a very straightforward formula. If I wanted to find the area of the sector, the same degree measure, all I'm doing is taking 1/2 times 4 squared times 40 pi over 180. Again, all I'm doing is substituting in my values. Yes, sir?
Why do you have to change the radius?
Because they're not dealing with degrees anymore. We're going to have pi in our answers. Okay, and when we're dealing with the trace stuff, we're going to kind of float, I don't want to say float, we're going to kind of veer away from degree measurements and go into radians, and that's when we're going to do the zeros.
So radius
Pretty much, yeah.
a little bit. A lot of it.
There was a half.
I just look later, I'll throw it up there for you. Okay. It's going to be some of the, just so these, so it's pretty much direct substitution, and then I'm going to talk about how we draw to get coterminal angles in radians as opposed to degrees, and that's kind of the weirdest part where you have to worry about your fractions and multipliers. Okay. So this should not be that scary. It's a lot of just direct substitution and going for it. Okay.
So is that the same answer?
It should. I don't think it is. I didn't do it. I mean, you get 16, so this becomes 8. 16 pi over 9.
Do we leave it in pi?
Yeah. Yeah, leave it in pi. And these are what the questions will look like. Again, they'll say the radius is 4, theta is 55, find the area, and find the arc length. So if I want to just do, I want to say the arc length is S, is R times theta, and then the area of the sector is 1/2 R squared theta. As long as you remember that theta is always written out in radians, it's very, very straightforward. 4 times 55 times pi over 180. Again, in this case, I can divide it top and bottom by 2. Yeah, how many 5s are in 90? 18, good. So there's 18 here, an 11 here, and then 2 goes into 18. So you get 11 pi over 9. If you're going to freak out by trying to simplify the fractions on your own, if you do use your calculator, you cannot put pi in your calculator and it will not simplify it for you. These calculators don't keep pi along for the ride. You'll have to just remember to put pi in your answer later. Yes, sir?
Wait, sorry, so you have two different numbers in the numerator.
Yeah,
So which one do you simplify first?
it doesn't matter.
You can go
Whichever
with-
one you can. Whichever one you visualize, whichever one, I don't want to say visualize, whichever one you decide to go with first. Myself, I saw a 4 and a 180. I can do them by 2, and I can do it by 2 again.
Okay, but it doesn't matter.
Yeah.
Either way. Nice.
And then I obviously saw that the 90 and the 55 are both by 5. There's a couple of ways you can go about it. Okay. Pretty much. This part, like I said, when we do the graphing of radians, that is what things get a little bit weird because you have to worry about your fractional amounts. This stuff is just plug and chug. It's really easy. Okay. So let's talk about how we graph radians. How do you graph? Well, what I want to do here is when we're talking about graphing of radians, I want to graph angles in radians. I want to remember my unit circle to start with. Now, I know yesterday I gave you guys all that, the unit circle to start to help out with the, as far as filling stuff in. What I want to do here is just kind of go back and look at it and rewrite some of the parts there, but not use the degree measures, okay? I want to get accustomed to talking about the unit circle in terms of pi. So, we know that this starts here at 0, and it ends at 2 pi. Everybody remember that? What here? Pi. What was here? And what was here? Good. All right. Those 4 values, 0, 90, 180, 270, are called the quadrantals. That means that they are on the axis. And we'll get into a little bit more of that stuff on Monday, just so you guys understand the vocab here. Now, the easiest stuff to do, since you just ticked off, basically, well, not ticked off, but you marked off the quadrantals, you marked off all your 90-degree angles. Well, what's the easiest one to cut that in half with? 45. So this becomes
Pi over
pi over 4, yeah. Okay. 3 pi over 4. Very good. Again, this is nothing more than just fractions here. Okay. What was the next angle we worked with? Remember? 30. We just did 45s. We did the 30, and you brought this up right away. 30 was what of 90? A third. So if I go to my 30-degree angle, it was a third of the 90-degree angle. So what was 1/3 of 1/2? 1/6. So we wrote it as pi over 6. Very good. So I had pi over 6. Now, do you remember the shortcut for going up 30 degrees each time? Just what? What am I adding? A sixth. Yeah. Everything goes up from 30 degrees, it goes up 1/6. It's 1/6 of the circle as you go all the way around. So 60 degrees is 2/6. 2/6 simplifies to be, so it becomes pi over 3. 2/6, 3/6, 4/6, 5/6. I'm going to go back and simplify fractions here in a second. 6/6, 7/6, 8/6, 9/6, 10/6, and 11/6.
Didn't we do this yesterday?
We did, yeah, we did, but what I'm doing here is just reminding you guys how the scenario goes as far as how it gets marked off. Because now you're going to start From there, all you have to do is simplify any of the fractions that you can. All right? So 4/6 is what? 2/3? These all work. This is 4/3. Okay. Let's see. I forgot what class it was, but somebody picked up on a really nice pattern if you forget how the denominators work. You all right? What do you got?
Where are all the sixths?
I simplify the fractions. 10/6 is the same thing as 5/3.
Yeah,
8/6 was 4/3. I just simplified it real fast. Okay? What I want you guys to see here, this is a really nice pattern if you're of the type that likes to visualize a pattern, because it does make things a little bit easier. Oops. 6, 4, 3, 3, 4, 6. 6, 4, 3, 3, 4, 6. It's math magical. Everybody see that?
Is the pi or 2
Yeah, it's 3/6. Okay. Everybody see that? 6, 4, 3, 3, 4, 6. 6, 4, 3, 3, 4, 6. Denominator plus 1.
Those are sixes, those are fours. Then you go through it.
Seriously? Did everybody hear this? Listen to this one again, louder.
The first quadrant is just pi over the thing, pi over the denominator. In the second quadrant, it's the denominator minus 1 times pi. And then in the third quadrant, it's the denominator plus 1 pi. And then in the fourth quadrant, it's the denominator times 2 minus 1.
That's I never saw that. That's pretty cool. Yeah, but if you remember,
I mean, he's really smart. That's really clever.
I know, but it's pretty cool.
Yeah.
So I mean, I know some people love picking up on patterns. It's a pattern. You picked up on it. All right. Denominator minus 1 in the second quadrant. Denominator plus 1 in the third quadrant. And the fourth quadrant just goes crazy. Denominator times 2 minus 1. That's awesome. Nice pickup.
times 2?
Never saw that before.
Times 2 minus 1.
Yep. Never ever saw that before. But I've been teaching this class for a while. Never picked up.
So if you memorize both those patterns, you just say.
Yes, sir. All right. Yes, sir. All right. And like I said, we're going to kind of revisit this quite often because it's kind of important. I haven't made mention of that yet. Maybe once or twice. Not always. All right. So here's what we've got to do then. Let's say I want to graph and find coterminal angles that are in radians. All right. Let's look at an example. Let's look at. No, that wasn't a coterminal. That was one.
Love that green radio.
13 pi over 2. I want to graph that and find a positive and a negative coterminal angle. Okay? This is, what's that? No, we're leaving everything in radians, my friend. I know, I'm a jerk, what can I say? I'd get over it.
Would you go back to the
Subtract 12 and subtract 1.
If you watch what's going on here, 2 goes into 13 how many times? 6.5. Okay? That's the same thing as saying 6.5 pi. Do you agree? Okay. If I said that this is 6 1/2 pi, how many revolutions does that? How many pies does it take to get around a circle? Two of them. So what happens here is that here's 2 pi, 4 pi, 6 pi, half pi. See what I'm doing there? I'm figuring out how many times around I'm going. What do we want?
It'd be 3 1/4. Because you divided it in two again because it's 2 pi for the whole 360. So you divide the 6.5 by 2, you get.
No. Stand up. Turn around 6.5 times.
Okay, this is.
You're still going, you're still counting. Okay, do you see how you're, hold on. What's happening here, if I take out 2 pi, that's 1 revolution, right? I have 4.5 pi left. Oops.
So then do you just multiply 360 by the amount of revolutions?
I'm not multiplying by anything. I'm not multiplying by any number of 360 here because I'm in radians.
Wait, what are we doing here?
I'm going to graph it. I'm going to graph it, and I want to find the coterminal angle.
Okay,
Right. If I subtract out 2 pi again, I'm left with half a pi. Half pi is at 90 degrees.
Good.
Oh, sorry, I thought I was already ahead of that.
So 3 revolutions and a half.
Yeah.
Okay.
So, well, it's half pi. Okay, so it's 3.25 if you think about it, because you're in terms of pi here. And that's where it gets a little weird. When you're dealing with the pi stuff, you have to remember that pi over 2 is a quarter turn, because 1 revolution is 2 pi. That's where it can get a little dicey. That's all. Okay. So at this point here, do you notice how we got to a positive coterminal angle? If I subtract 2 pi from that right now, what would be the negative coterminal angle? Well, if you had
negative.
if you had 50 cents,
Negative 3 pi.
yeah, 3 pi over 2, yeah. If you only have $3, or excuse me, if you only have 50 cents and you need $2, how much are you short? $1.50, 3.5, 3 over 2. So the negative would be 3 pi over 2. Another thing you could always do is you could always work with common denominators. If you're looking at it in terms of the pi, it was what, 13 pi over 2. And if I want to subtract 2 pi, that would be, what, 4 pi over 2? Is it 4 pi over 2 the same thing as 2 pi?
Yeah.
If I subtract 4 pi over 2, I'm going to get 9 pi over 2. Subtract it again. I get 5 pi over 2. I subtract it again. I get pi over 2. And that's within 1 revolution.
Where'd you get 4 pi?
Common denominator. 2 pi is 1 revolution. Remember how when we did degrees, they're subtracted by 360? Here I'm subtracting that by a radian. Yeah, absolutely, absolutely. Okay. Now, there's 2 ways of going about that. Yes, sir.
On the negative 3 over 2 part real fast.
What I'm doing here again is when you wound up at your positive coterminal was here, in order to get there going the other direction is that way. Yeah. All right. So one way that I think a lot of students see this better is, in fact, by using this common denominator. You're shaking your head, I know, but a lot of times people, even though it's working with fraction, it's not as bad as your back because what you're doing is you're unwinding your revolutions. Okay? me show you another one. First thing we want to check. First thing you want to check is what is 14? How many times does 14 go into 17? 4 1/4, right? So is that more than a revolution? Yep. It is. So what I'm going to do here, since this is going to be more than one time around the circle, I'm just going to write it 17 pi over 4, and I'm going to subtract out 2 pi. But instead of subtracting 2 pi, I'm going to subtract it with a common denominator. What would be 8 pi over 4? What is 2 pi as a fraction of the common denominator of 4? Okay. So what's 17 minus 8? 9. 4 goes into 9 how many times? Twice, and there's leftover, isn't there? So is that still more than one revolution? So we have to back out one more round. What's 9 minus 8? So it's pi over 4. There's your positive coterminal angle. Subtract 8 pi over 4 again, what do you get? What's 1 minus 8? Very good. If you go again, there's your positive, there's your negative.
You don't have to write in degrees, you write it in that.
Yep. Yeah, if it's given to you in radians, you stay in radians. If it's given to you in degrees, when you're talking about positive and positive, negative coterminal, you keep it in degrees.
Is there ever going to be a time when you have to take those and then convert them to English?
Like in degrees?
Yeah.
Yeah, it'll say, yeah, there'll be a question that says convert this to degrees.
Okay.
There will be a question that'll say to do that, and you'll have to do that without a calculator. Oh, come on.
So that's 45 degrees, the pi over 4.
Right. Yes. Yes.
What if 17, it can't go into 4, like it's
3 goes into 17?
No. If the numerator is like, if it's less than the denominator, what do you do?
Oh, okay, all right. Great question. If it happens to be 3 pi, we'll make it a little bit easier, over 5. Does that make sense? And I want to find a positive and a negative coterminal angle. 3 pi over 5, that's well within one revolution. We all agree on that, right? Yeah. So what I'm going to do here is I'm going to add 2 pi, and then I'm going to subtract 2 pi. But instead of adding 2 pi, I'm going to add it in terms with a denominator of 5. So what's the same thing as 2 with a denominator of 5?
10 pi over 5.
Very good. So I'm going to add to that, and I get 13 pi over 5 for my positive. I take 3 pi over 5, and I'm going to subtract 10 pi over 5.
7, 5.
Negative 7.
Yeah.
Notice it's basically the same exact scenario if you had 30 degrees. You add 360, you subtract 360. Here, you're just trying to turn 2 pi into a fraction that you can easily manipulate. Okay? Does that make sense?
Yeah.
It's a good question. Yes, sir? We'll come back. We're getting there.
If you're finding a positive coterminal, why does it matter? Like if you had to do why does it matter?
It's the general rules we want to keep within one revolution to start with.
Three divided by 5.
The real reason is because eventually we're going to start talking about both reference angle, and that's kind of the basis of it. We want to get within one revolution system and find that refraction angle, and that'll be on one hand. That's why I'm just trying to get you guys the habit of, I figured out exactly where it's going to sit within one revolution of the circle, because that'll be easier to find exactly off of what axis you're on. So you start with 360. Yeah. You just keep adding it back and forth. And eventually, this coterminal stuff comes back to play when we do this.
From the 3/5, that's add 2 pi.
Oh, forgot to quit. When we start doing that. Because then I'm going to put boundaries upon it within one revolution or infinite revolutions. Because, like, you're right, every time you come around to the same spot, you're basically adding pi to it, or 2 pi to your possible answers. And we're going to get to that in chapter 14.
So then,
What I will, yeah, it'll say, just like the book does, find one positive, one negative coterminal answer. It's not stupid. That means you're learning.
Wait, is 0 like the whole term? I thought 0 isn't actually a positive or negative.
It's a weird one. We don't really spend a lot of time defining coterminals and quadratics. We use the quadratics to improve all the data on the axis. You just got to about, oh yeah.
And how do you spell that?
Sounds really cute. All right. Again, let's go back to thinking about the graph then.
Take 4 and you multiply it by 2.
What I'd like to do is find out where this angle will lie. So I have 2 pi over 9. And when I'm graphing that, really when you're dealing with radians, you're going to be asked to figure out what quadrant does that lie in. So is 2 over 9 smaller than 1/2? So it's somewhere in here. So what quadrant is that? Okay. That's what you're looking at being able to do. Can you recognize the fractional amount to be within one of the 4 quadrants via the idea of 1/2, 1, 3/2, and 2? That's what you're looking at, figuring out where it goes. If it happens to be an angle that is more than 1 revolution, you're going to want to try to back it in to figure out what the positive coterminal is, so you can figure out the idea of what quadrant it lies in. All right. This is graphing the radians. It's actually quite simple. All right. There's really not a big trick to it.
We only have to do an approximation.
Yeah, I'm not going to measure it out with something. Sure.
All right.
Thank you for the snicker there.
No problem.
All right. I want to graph this. Negative 5 pi over 6. If I'm going to graph negative 5 pi over 6, am I going clockwise or counterclockwise? Clockwise. Now, think about 5 over 6. Is it more than 1/2?
yes.
Is it less than 1?
Yes.
So what quadrant is it in?
It's in the third.
Very good. Not bad, is it? The idea here is, again, you're just trying to figure out which one is it bouncing upon, because now, and this is where we're going, the reference angle to this is how far off of the y-axis is that? Unless what's the reference angle on that?
Either 1/6 or negative 1/6, right?
Which is it, Mark?
Yeah, which is it?
1/6?
Negative 1/6.
Or is it pi over 6?
And 5 or 6.
Yeah, 5.
All right, Mama, what's the sign of that?
That's a pretty cool number.
The sign of that?
Uh-huh. You should know this. You've taken this.
Oh, the sign of pi over 6?
Negative 5 pi over 6.
Oh, man, this is so hard.
Well, is it going to be positive or negative?
It's going to be
What quadrant is it?
negative.
It's negative. Very good.
Yeah. Okay, what was the next question, guys?
I didn't mean to catch you off guard because I know you've done this. That's why I want to make sure. He had to do this for the EMSA stuff, so he's seen some of this. That's why he thinks he's cool because he knows some of these answers. All right. Let me give you guys a few problems in this to try out for tonight. Nothing too crazy.
No, I swear to God, if you did,
So why couldn't I have this?
Yeah, if it's more than one lesson, more than half lesson, more than half,
All right. Those first four, again, are finding positive and negative coterminal angles. I did ask that you just graph the original angle in radians as well. It doesn't say to do that in the book, but I figured those are four that are right there. You can just graph them and then find your positive and negatives. The 60 through 65, those 6 problems are finding the arc length and the area of the sector given information in radians. They fly right through that. The last couple are a few of the very, very, very easy word problems with these things. They give you diagrams and explanations. You're probably working with arc lengths and some circumference stuff. We're talking about time of the plot. I think one of the questions is, how many revolutions in radians does the clock turn while you're in school?
Too many times is the answer.
How many radians is in a school day?
Well,
How long is it?
16.
Well, think about it. It's really easy. 7:45 to 2:45, right? So
8 hours.
8, 9, 10, 11, 12, 1, 2. There's 7 revolutions. How many pies are in a revolution? 2. What's 2 times 7?
14!
Yay!
I was thinking about that.
How much time do you have left?
I was just talking about the hour hand. They might ask you about the second hand on that one too. I don't know.
That would actually my brain hurt.
That was the best answer ever. Seriously, just under your breath.
That's too much work.
Really?
Multiply it by 60.